Hey, what's up? I'm Dave Boyer, aka Mr. Boyer, aka the Swamp Man, here at my classroom, Kernersville Middle School, and get to teach you a little bit of some e-learning in the next couple of weeks. So, my lesson today is going to be on the theory of continental drift and a look at kind of what the tectonic plates are like today. So let's go ahead and go over some lesson objectives here. I'm going to begin by talking about the theory of continental drift. We've already discussed that in class before we went out on this break. We're going to talk about Alfred Wegener and the evidence that he collected with continental drift. We're then going to look at the map of the plates that we have today and label those plates, talk about how they're named, and then we'll finish today's lesson with understanding how convection currents in the mantle are driving those tectonic plates and moving them around the Earth. So it may be hard to see with the GoPro kind of taking a video here of the Promethean board. It's probably a little bit flashy, but hopefully we can still look at it and still understand what we're seeing. So Alfred Wegener in the late 1800s, early 1900s, wrote books on the theory of continental drift, was the first to kind of lay it out. He really struggled some with providing the evidence for that. He kind of had this idea, and it was through collaboration with other scientists that he was able to start forming the evidence of it. And today, we have way more evidence from the advanced technologies that we have to study the plates and the insides of the Earth, and his theory has been upheld by modern science. So looking at a long history, 250 million years ago, the continents were connected together in a period of time in a region called Pangaea, Pan meaning all, Gea meaning Earth. So all of Earth was connected together in one landmass. And then that landmass began to break up over the millions of years. So we get the division of Pangaea into a northern part and a southern part, the Laurasia in the north and Gondwana in the south. Over the next several million years into the Jurassic period, we've got dinosaurs on the Earth. They're on these continents as those continents are sliding away from each other. But this process is really slow. Millions of years we've already been talking about, and the continents have hardly even separated. So it's not like the dinosaurs were riding these like a surfboard and they were feeling like they were really cool. Continents continue breaking up into the next period, the Cretaceous period, 65 million years ago. And then it gets us to present day where we have our 7 main continents. So we're going to go ahead and switch to a map of the world that is today. So we've got our continents like I grew up studying: North America, South America, Asia, Africa, Asia, Europe, Australia, and Antarctica. And they are in the places that they are because they've moved over those millions of years after the breakup of Pangaea. Life on those continents have adapted to where they are. We got the equator here, and the further away from the equator we are, we just studied this in our seasons unit and the space unit. Further away from the equator you are, the colder the temperatures, the less direct sunlight they're receiving. So plants and animals and organisms are going to adapt to the situation that they're in. And that kind of brings us to Alfred Wegener, his theory of continental drift, and which evidence he began to collect. His first piece of evidence that he saw was looking at a map. He was looking at the eastern side of South America and the western side of Africa. And this little turn in the continent right there, that just seems like South America fit in perfectly there. And that was his first kind of idea that made him think, man, maybe these plates were once connected and they've drifted apart. He didn't understand why or how they would have done this. But his next step was to start to talk to some other people and collect some more evidence. Some of the main people he talked to were the paleontologists, paleobotanists, people studying fossils on different areas around the continents. So these are some of the continents of the southern hemisphere as they were connected together in Pangaea 250 million years ago. And each of these different creatures are extinct now, but there's fossil remains of them in different areas. So scientists at the time of Alfred Wegener were finding fossils from reptiles, lizards that were found on different continents like South America and Africa. If we look back at the map of the world, when we look at South America and Africa, they're separated by this huge stretch of ocean, the Atlantic Ocean, thousands of miles of ocean between them. And a reptile, being a cold-blooded animal, is not going to be able to survive swimming across a cold Atlantic Ocean. So there's no way that those organisms could be found on multiple continents unless there wasn't an ocean between them at one point when they were there. Similarly, some of these plants, like this fern right here, Glossopteris, this fern can be found even on parts of Antarctica. Antarctica today we think of as this really cold and harsh environment that plants aren't able to survive on. But Antarctica wasn't in the same place that it is today, back when Pangea was together. So that fern was able to survive there, Australia, South America, on the subcontinent of India, Africa. So this fern was widespread. Well, ferns spread by spores, these little seed-like things, and those seeds can't float across the entire ocean and then germinate and grow into a new fern in a new world. They would need to have connections of land. So that was some evidence that Alfred Wegener was able to put together and supported his theory. Scientists since then went through other lines of evidence. That's the wrong map. Other lines of evidence like the mountain chains. So we had a connection between this is the Appalachian Mountains running along the eastern seaboard of North America up into Greenland, and the mountain ranges of the west side of Europe. All are from rocks came up out of the mantle in the same time period, or were crushed together and formed into metamorphic rock in the same time period. So this mountain range was at one time connected together, since it's been separated apart by the Atlantic Ocean. Further evidence of that. So his theory, Alfred Wegener's theory, was supported each and every step of the way by new science that was coming out. So let's take a look at our map that we have today, our tectonic plates. So as plates have been moved by the convection currents underneath them, which we'll talk about, plates continue to crack and form into smaller plates. They're crashing into each other, they're pushing on each other, they're spreading apart from each other. There's tons of movement of plates. So as we look at some of the names of plates, we get plates that are named for oceans. Like here we have the Pacific Plate, which is the largest plate. It contains the entire Pacific Ocean. On this map, it stretches from one side to the other because we've got a globe and not just a 2D map. Some continents have their own plate named after them. So we've got the African plate right here. We've got our North American plate up here, South American plate underneath it, and so on and so forth. So plates can be named from oceans. They can be named from continents. In some cases, they can be named from smaller bodies of water, like we've got the Caribbean plate here, named for the Caribbean Sea. We also have some plates that are named for regions or countries as well. The Philippine plate that's here, it's its own kind of smaller plate nestled right in between the Pacific plate and the Eurasian plate. And then there's some of the smaller plates that are named after peoples. We have like the Nazca plate that's here, named for an indigenous group of people in South America. The Cocos plate, pretty similar to that. And then there's plates that are named for famous people or explorers or scientists that studied them. One of my favorite to look at is this tiny little plate on the west coast of North America, running right by the Pacific Northwest with Washington and Oregon, and it's got kind of a funny name. It's the Juan de Fuca plate, named for a guy that discovered and worked with plate tectonics in that area. So there we've got our main plates. You're going to be completing an activity where you're matching up names of plates with in a website. So the last thing to talk about is why these plates are moving, what's causing them to move. One of my favorite areas to look at is definitely this spot right here in between India, the Indian plate, and the Eurasian plate. India, when we had the breakup of Pangea, broke off of the coast of Africa and has been moving the fastest plate. It's been moving to the northwest really quickly, 10, 12 centimeters every single year, which sounds pretty small, but in terms of a giant piece of land moving, that's pretty quick. And it has slammed into the Eurasian plate, and that pushing has formed the Himalayan mountains along this border between India, China, Pakistan, and Nepal. Some of the most beautiful mountains in the world. So each of these plates are moving, and the thing driving them is convection currents in the mantle. So let's go ahead and talk about those convection currents. So if we have some surface of the Earth right here, we would be up here above that. We've got a thin layer of crust, maybe as much as 100 kilometers thick, but in some areas down to about 40 kilometers thick, and that's going to be solid rock. And that crust can be broken apart into these different plates, and each of those plates could be moving separately from each other. But underneath those plates is the mantle, a liquid layer of rock, and the mantle has convection going on. So we have to understand the convection currents in the mantle. We need to look below that at the core. So one thing that we learned about the core in our previous unit is that the core is exceptionally hot. The inner core can get as hot as 10,000 degrees Celsius. It's as hot as the surface of the sun. So this incredible heat at the bottom of the mantle being supplied by the core is causing the liquid rock in the mantle to rise. But the core is not equally hot in every single spot around it, so we have unusually hot spots. I've drawn one right here in the middle of the screen. And there can be dozens of these spread around the globe. As the magma there gets heated up and becomes less dense, it rises away from that area, rising up towards the top of the crust. Well, at the top of the crust, it's going to spread out due to differences in pressure. As we have magma rising up and hitting this top spot right there, that's more mass into the same volume, so the density is going up and the pressure is going up. Well, outside of that area, we have lower pressure, so the magma needs to spread out and find its way towards lower pressure. It's also going to cool down as it gets away from the core, so eventually that magma is going to sink back down towards the bottom of the mantle. Just like before, if we have more mass coming down into a space, it's going to increase the pressure in that area. Well, that hot spot that was causing the magma to rise and leave that area is going to create lower pressure where that rising magma is. And that's going to allow that magma to be drawn back in towards the hot spot and then heated up by that 10,000 degree inner core, causing it to rise and continue the cycle around and around and around. So again, there's dozens of these convection currents happening in the mantle. And our main focus for most of this unit is going to be what's happening to this crust up above it. So let's take a look at some of these pieces of crust. Look at this spot here that I've kind of sectioned out. That crust is floating like a raft on the ocean, this ocean of magma. And if we see at the top right here, this magma is drawing over away from the hot spot. So the arrow is carrying that to the left. This piece of crust is going to move to the left. Over on here, we have another piece of crust that's been broken apart. It's free to move independently from the rest of the Earth, and the convection current is drawing it away from here. So here we have two plates that are moving in opposite directions. And the combinations of these convection currents, if we had another one over here, possibly that's connecting here with a magma pulling over, dropping down as it cools down, then getting sucked back in towards a different hot spot, that piece of crust is going to move to the right and crash into this one. Every single connection between one plate and another are constantly having interactions like this, either being pulled apart, slamming into each other, or sliding past each other side by side. So a big idea right here. Convection currents in the mantle are driving each of those individual plates that we were just looking at and pushing them around the planet and causing major changes to our surface. So we'll get more into those changes as we go. Just wanted to stop and share that with you and tell you that science rocks.
Actually, PE rocks, guys.
Peace.